Okay, and I'm just going to show you a graph of that, something which is interesting to look at.
Professor,
Yep.
when EVXY equals x minus 1 dx plus c, where did the x minus 1 come from?
Oh, the integral of x e dx. We did that before.
Oh, okay.
Yeah.
Integral of both sides. Okay. Oh.
Did I get these pop-up windows here? Crazy. Okay.
That's asking you for the network connection?
Yeah, yeah. Let's see. Good, okay. So what do we got? Solution someplace. Here, x minus 1 plus 5 e to minus x. You see there it says x goes to plus infinity. That thing is kind of dying out, and it looks like it approximates a straight line, x minus 1. Okay?
Is the dashed line?
Yeah, exactly.
Okay.
Okay. So basically, there's the solution, right? What I did is I left C in there kind of arbitrary to, at first the general solution. And here's some things you can see for C positive, they look like that, for C negative, like that, okay? And our solution has the value C equal to 5, I think, right? So I guess maybe it's one of these guys or something. But you notice that no matter what the value of C is, as you go to plus infinity, the dashed line I drew was y equals x minus 1. And you can see from the equation, regardless of the initial condition, as x goes to plus infinity, the e minus x dies out, and all those guys approach a straight line, y equals x minus 1. Okay, just want to show you that. Okay? Like I said, in much more complicated situations, it's a very good idea to basically integrate your analytical results with computer stuff or numerical, so that it gives you more of a confidence in your answer, right? Because we're all humans, you can make mistakes. Okay, I've done that many times, and when you see something like this, you're pretty confident you have the right solution, right? So much for that example. I think I should finish one more, and that'll be it. Okay. I finished a little bit earlier today, which is fine. Okay. Put this back on. Hopefully this won't be too annoying if I can somehow let me just put this to sleep. Okay, fine. Okay. I don't mind it back that background like that. I can live with that. Let's just go over here. There's nothing. Okay, here's the last example. Okay. Many times in applications you get differential equations where some of the coefficients or some of the functions appearing actually are discontinuous. Okay. Give an example that I won't go too much off onto a tangent over here. When you take mechanics of materials, elasticity, you'll be dealing with things like a beam, okay, that's deflected. This is basically the beam. I'll draw it a little thicker over here. The theory of that you deal with in undergraduate courses usually is what's called thin beams, where the cross-sectional dimensions are small compared to the length. And you're going to be looking at things like, this thing's under certain types of loads, okay? And it's going to bend, okay? And what happens is that many times you could have a discontinuity in certain quantities. For example, like there could be a support over here, okay? So there's a point load here, no load here. It could be a distributed loading over here, like like the cable we did, okay? And what happens is that you'll find out that the differential equations that you get many times have terms in them which represent physical quantities which are discontinuous, okay? And matter of fact, it's well known that if you have a beam and you have a point load, so like I have a beam and then I support it over here, say on some structure, actually there'll be a jump in the bending moment across that. There'll be a discontinuity in the shear, rather, not the bending moment. There are other cases where the bending moment is discontinuous. If you have like a spring connection on the beam, okay? So it's not uncommon to have discontinuous functions in applications. It's not just a mathematical, the thing people do just to investigate for its own sake. So what we're going to do now is look at an example where there is a discontinuity, and it'll be the following. The equation, its appearance will be very simple, but to solve it, we'll have to do a little work. Let's do dy dx plus y, okay, equals some function f of x, okay? And what is this f of x? Okay, this could be like the loading term, let's say, on the beam. It's given in pieces. It's 1 if 0 is less than or equal to x less than 1, less than or equal to 1, let's say, and it's 0 for x greater than 1, right? So if you were to plot f of x versus x, here's 0, here's 1. Between 0 and 1, it's 1, right? And then it would drop to 0 for x greater than 0, okay? So what we have is a differential equation. The coefficients are very simple. They're 1 and 1 on the left-hand side, but the loading term, if you want to call it in engineering speak, or the inhomogeneous term, mathematical terms, has a discontinuity at x equal to 1, okay? Well, it's a first-order equation. I want to get a unique solution, and I wanted to go through the point y of 0 equal to 0. I want to go through x equals 0, y equals 0, okay? Now what's going to happen is that we're going to solve this equation in two parts. We're first going to solve it in the region between 0 and 1. That'll give us one solution, okay? See, because the f of x changes. You can't solve it in one sweep, right? Because what's f of x? So first we're going to restrict ourselves to the domain between 0 and 1. We'll get a solution. Then we'll get a solution greater than 1, okay? But there'll be an indeterminacy in there, and the question is, how do you match the two, okay? And sometimes that matching condition is based on physical conditions. In our case, suppose this was something like a beam that doesn't break, okay, even though it's it's not really a beam. You want continuity, okay? So I'm going to demand that the solution to this equation, y of x, be continuous at x equal to 1. So even though the loading is discontinuous, I want the solution to be continuous. And that would be a physical condition, right? If you had a beam, right, and you did have a point load someplace, unless the beam breaks, there's not going to be a break in y of x, okay? So y of 0 equals 0, and we want y of x continuous, specifically at 1, right? Continuous, okay. Okay, so let's see if we can get this done. Okay, so the first case basically we're going to do is just look at 0 less than x less than 1, x between 0 and 1. Okay, well in that case the differential equation becomes dy dx plus y is equal to 1, right? Because we know what f of x is on that interval. Okay? Let's just do this kind of quickly, right? We know the integrating factor is y. It's basically e to the x, right? So I get e to the x dy dx plus e to the x times y equals e to the x. Okay, we know the left-hand side is just d by dx of the integrating factor times y. Check it, yes. That equals e to the x. Okay, let's integrate. E to the x times y is equal to the integral of e to the x, which is e to the x plus an arbitrary constant. Okay. Or y equals, divided by e to the x is 1 plus a constant e to the minus x. Okay. Now I want the thing to go through 0, 0. Now, this is very important to note. This solution is valid between x equals 0 and y equals 1. Sorry, x equals 0 and x equals 1. So therefore, I can apply the initial condition to this piece. Okay? Because I know y is 0. Y is 0 has to equal 0. So I get 0 equals 1 plus c1. Therefore, c1 is equal to -1. Okay? So the solution for the first domain. So, and you have to be very careful. You may want to do a different letter. For 0 less than or equal to x less than 1, the solution y of x is equal to, if I say c is -1, 1 minus e to the minus x. Okay. Now we got to do the other part.
So only fx follows our domain for our x?
In other words, what happened is that because f of x changed, I basically have to solve it in 2 pieces. Okay? So let's just say that's one part. Okay. Now let's do the second part. What happens now for x greater than 1? Okay? For x greater than 1, the differential equation becomes dy dx plus y is equal to 0. Right? Again, the same integrating factor, right? It's e to the x. So I got now d by dx of e dxy is equal to 0. Before it was equal to e to the x, right? Again, if I do that, I get e dxy prime. Okay? So now, when I integrate that, I get e dxy equals an arbitrary constant, let's call it c2. So y now looks like some constant c2 e to the minus x for x greater than 1. We got to get that c2 now. Now, I cannot use y of 0 equals 0, right? Because this solution is only valid for x greater than 1. Okay? Remember I said you need another criteria? I use the continuity now. Okay? I have this solution over here, which is valid between 0 and say 1 minus epsilon, approach 1 from the left. This thing is valid for x greater than 1. Let's match them up at x equal to 1. Okay? And that's basically, then we'll be sure that when we look at our solution graphically and when we plot it, there'll be no break at 1. Okay? You'll see there'll be a break in the derivative. It's very interesting. The derivative will be discontinuous, but there'll be no break in the function itself. So, at x equal to 1. Well, from the first case, if I approach 1 over here, I find that the solution x equal to 1 is 1 minus e inverse, or 1 minus 1 over e, right? What happens when I go and approach x equals 1 from above? I use this solution, I get c2 e inverse, right? So therefore, c sub 2, I multiply through both sides by e inverse, and I multiply by e, I get e. This is so simple, I want to multiply through by e. So I get e minus 1. That's it. Okay, so now y of x in the other interval is known. Okay? It's equal to e minus 1, right? E to the minus x. Right? For x greater than or equal to 1. Okay? So here's the whole solution. It's that part and this part. Okay? So for x between 0 and 1 inclusive, it looks like 1 minus e to the minus x. And for x greater or equal to 1, it looks like that. And of course, we calculated the constant over there such that the solution is continuous. If you evaluate this thing at 1 and that at 1, you get the same result, namely 1 minus e to the minus 1. Okay? So let's look at the graph of this, okay? And then this will just we'll pull it quiz for today. So f(x) is continuous, okay? So remember, I forgot what the formula was. We had a certain thing between 0 and 1. So that's the graph from here to here. And then there was another solution. It looked like the dying exponential for x greater than 1, which is that. And you'll see how the slope is discontinuous at x equal to 1. Okay? And again, a physical manifestation of that would be if you had like a beam with a point load on it, there's always going to be a jump in the shear force. Okay? And in fluid mechanics, this carries over where there are other things where you get this kind of shock waves. Okay? So we do have situations where either a loading condition or some physical factor is discontinuous, and that leads to solutions that have this kind of weird behavior. Sometimes the solution is discontinuous. Most of the time the solution is continuous, but its derivatives display discontinuities. And those derivatives have physical interpretation. Okay, so there's your graph for all values of x greater than or equal to 0. It goes through the origin, okay, as we desired. It's continuous at x equal to 1. Basically, that's it. Okay, so this actually finishes this module on first order linear equations. I'll probably post a homework later today, so be on the lookout for that. And then, like I said, we have, before the first exam, another topic is called exact equations, okay? And so I imagine, we'll finish that probably next week by next Wednesday. Okay, so I'll see you guys on Monday.